In this video, we shall look at a few review problems associated with electric potential energy. Problem 1. At a certain distance from a point charge, the magnitude of the electric field is 500 volts per meter, and the electric potential that charge creates at that distance is minus 3000 volts. If a second point charge of 1 microcoulomb, a positive charge, is placed at a distance r equals to 10 meters from the first point charge, find the electric potential energy of the system. So our first task is to determine the magnitude of the first point charge. Let's call that point charge Q. We know it's a negative point charge because the potential is negative at a particular distance. So let's say that distance is r. The electric field at that distance is 500 volts per meter, and the potential there is minus 3000 volts. First, we need to figure out what Q is. Since the magnitude of the electric field is given by that expression KQ over R squared, and that is 500, we also know the electric potential is minus 3000 volts. So the minus in the minus 3000 volts tells us that this charge is a negative charge. However, let's just look at the strength of the potential or the magnitude of the potential. KQ over R is 3000 volts, and that is equation 2. Now let's take equation 1 divide by equation 2. So the left hand side is just KQ over R squared divide by KQ over R, or R over KQ. So KQ goes away, this R will cancel that R, and the right hand side is 500 over 3000, and that is just 1 over 6, meaning R is 6 meters. Substituting R in, let's say, there, we can get Q. And how do we do that? K is 9 times 10 to the power 9 in SI units. Q we don't know. Over R squared, so 6 squared, so that is 36, equals 500. And you can determine the strength of this charge, that negative charge right there. After doing the calculation, the strength is found to be 2 times 10 to the power minus 6 coulomb, or 2 microcoulomb. Of course, to be more accurate, it has to be a negative charge. So Q is minus 2 microcoulomb. Having found the strength of the first point charge, we can proceed to determine the electric potential energy of a system that consists of another charge, namely positive 1 microcoulomb at a distance 10 meters from the first charge. So if, let's say, at a distance 10 cm from the first charge, you have a second charge with a strength of plus 1 microcoulomb. What is the electric potential energy of the system? Since this system consists of only a pair of point charges, the expression is just K times the product of the two charges, minus 2 times 10 to the power minus 6, times 1 times 10 to the power minus 6. So this charge is there, that charge is there. Over the separation distance 10 cm, convert that into meters, 0.1 meter. And that's going to give you the potential energy in joules. When you do the calculation, you would get minus 0.18 joules. We emphasize that we have used the following equation. The potential energy of a point charge, let's say point charge 1 and point charge 2, is given by K, the product of the strength of the two charges, over the distance between the two charges. Problem 2. Find the amount of work required to assemble 4 identical point charges of magnitude capital Q at the corners of a square of side D. So initially there aren't any charges at the corners and you bring in one by one, say to this corner followed by that corner and then that corner and that corner, and you finally end up with such a configuration of charges: Q, 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 Q. So the idea is, of course, the work required to build such a system of charges must be the same as the electric potential energy of the final system. So let's just calculate the electric potential energy of such a system. Let's label this charge to be charge 1, this is 2, this is 3, and that is 4. In order to calculate the potential energy of the system, we need to consider pair by pair. So the first term is, say, pair 1, 2, followed by pair 1, 3, pair 1, 4, pair 2, 3, pair 2, 4, and pair 3, 4. We stress here each pair must be considered only once, so terms like U21 need not be considered because the pair 1, 2 has been taken care of by that term U12. Likewise, if you look at U24, you don't need or you should not consider U42 because the pair has been taken care of by the term U24. So we should avoid counting a pair 2 times. So let's write down the terms. U12. U12 is K times the product of charge Q1 and Q2. So both have strength of Q, so Q squared. The distance between them is D, so D. Now let's look at 1, 3. 1, 3 is separated by that distance. So the product of the two charges is Q squared as before. The distance there, that's a diagonal distance using Pythagoras theorem, is square root 2 times D. So here is over square root 2 times D. Now U14. 14 is between that and that. It is just K Q squared over D. The separation distance between them is D. Now 2, 3, this charge and that charge will give you another term, KQ squared over D. 2, 4, that's these two charges. Separation distance is square root 2 times D. So the term is KQ squared over square root 2 times D. And finally, U3, 4, this charge and that charge. And that will give you KQ squared over D. Adding together, you have such term, 4 of them all together. So 4 times KQ squared over D, and 2 terms with square root 2D in the denominator. So that means 2 over square root 2 KQ squared over D. And this can be simplified in the following manner: 4 plus 2 over square root 2. And from that result, this is the amount of work required to assemble such a system. And this solves the problem. Problem 3. An electron starts from rest 3 cm from the center of a uniformly charged insulating sphere of radius 2 cm with a total charge of 1 nanocoulomb. So an electron, labeled as E there, starts at a distance 1 cm from the surface from rest. So at that point, the speed is 0 meter per second. We want to determine the speed of the electron when it reaches the surface of the sphere. So as the electron goes all the way like that, and when it gets to the sphere, what is the speed U? This is the uniformly charged insulating sphere of a radius 2 cm, and the total charge is 1 nanocoulomb. We can use conservation of mechanical energy to solve this. Let's call the starting point as the initial point and the surface of the sphere the final point. From conservation of mechanical energy, the mechanical energy initially must be the same as the mechanical energy at the final state. So the initial mechanical energy, namely the mechanical energy there, consists of two terms, the electric potential energy and the kinetic energy there. And at the final state, the final electric potential energy and the kinetic energy there. We know the electron starts from rest, so that means the initial kinetic energy is 0. The potential energy, or the electric potential energy of the electron when the electron is 1 cm above the surface, is given by K, the product of the two charges. Electronic charge, we know it is minus 1.602 times 10 to the power minus 19 coulomb. The other charge is plus 1 nanocoulomb, so 10 to the power minus 9, over the distance between that electron and the center of the sphere is 3 centimeters, so 0.03 equals, let's calculate the final electric potential energy, namely when the electron is at the surface of the sphere. So that is given by, again, K. We remind you that K is 9 times 10 to the power 9. The product of the two charges, minus 1.602 times 10 to the power minus 19, that is the charge of the electron. The charge of that insulating sphere is 1 nanocoulomb, so 10 to the power minus 9. The distance between them, the center to center distance when the electron is there, is 2 centimeters, 0.02. The final kinetic energy of that electron is given by half the mass of the electron is 9.11 times 10 to the power minus 31 kilograms times the speed squared. The speed, which is what you want to determine, is taken to be u, so u squared. You see that the left-hand side is that, the right-hand side is this term plus that term. So the only unknown in this equation is u, and we can solve for u. We remind you that K is given by that number. And when you solve for u, you get the following number. U is 7.26 times 10 to the power 6 meter per second. And that solves the problem. As always, thank you for watching.